First extension theorem. We already discussed about the general construction of probability model, and it includes two extensions, first and second one. Here we discuss about first extension of general construction. Before that, we want to know about the structure A of S, or the algebra generated by S. For that, we have a lemma. The field generated by a semi-algebra. Suppose S is a semi-algebra of subsets of omega, then A of S equal to set of all summation I belongs to I, Si, capital I is finite, and set Si belongs to capital I is disjoint, Si belongs to S. Is the family of all sums of finite families of mutually disjoint subsets of omega in S. That is, we want to prove that A of S is the set defined here, that is set of all sums of finite families of mutually disjoint subsets in S. Proof. Let lambda equal to set of all summation I belongs to I, Si, capital I finite, and Si belongs to I disjoint, or Si belongs to S. Now we prove that lambda is equal to A of S. For that, first we want to prove lambda is a field or an algebra containing semi-algebra S. For first take singleton X belongs to semi-algebra S. Clearly it is a finite set and it is disjoint. So it is in lambda. That is, S is contained in lambda. Now we claim that lambda is a field. To prove the claim, we want to check the field postulates. First one, clearly omega belongs to S. So omega is in lambda, since S is contained in lambda. Second one, let summation I belongs to capital I Si and summation J belongs to capital J Sj dash be in lambda. Here I and J are finite set A, and Si belongs to I, Sj dash J belongs to J are disjoint subsets of omega in S. Now consider the intersection of these two elements, which is equal to summation ordered pair Ij belongs to I cross J, Si intersection Sj dash. Since Ij are finite, I cross J is a finite set A. Also Si intersection Sj dash, Ij belongs to I cross J is a disjoint subsets of omega. Since Si Sj dash belongs to S, and S is also a semi-algebra, S is a pi system. So Si intersection Sj dash belongs to S. Its finite intersection is in S. Then summation ordered pair Ij belongs to I cross J, Si intersection Sj dash belongs to lambda. So lambda is closed under finite intersection. Now we prove it is closed under complementation. Let A belongs to lambda. Then A can be written as summation I belongs to capital I Si. Then A complement is equal to summation I belongs to I Si whole complement, and that is intersection I belongs to I Si complement. Here I is a finite set and Si belongs to I are disjoint subsets of omega in S. Since Si belongs to S and S is a semi-algebra, its complement can be written as Si complement equal to summation J belongs to Ji Sij, where Ji is a finite index set and Sij J belongs to Ji disjoint subsets of omega in S. Then clearly is complement equal to summation J belongs to Ji Sij belongs to lambda. But lambda is closed under finite intersection. We have intersection I belongs to I Si complement belongs to lambda. That is, A complement belongs to lambda. For finite union, let AB belongs to lambda then A complement B complement is also belongs to lambda by above, which implies A complement intersection B complement is in lambda, since it is closed under finite intersection. Hence A union B whole complement is belongs to lambda, that is, which implies A union B belongs to lambda. That is, lambda is closed under finite union. Therefore, lambda is a field containing S. Since A of S is the smallest algebra containing S, A of S is contained in lambda. Put it as 1. Now to prove lambda is contained in A of S, let A belongs to lambda. Then A equal to summation I belongs to capital I Si, where I is a finite index set and Si belongs to I are disjoint subsets of omega in S. Since Si belongs to S, for all I belongs to capital I, we have Si belongs to A of S, since A of S contains S, which implies summation I belongs to I, Si belongs to A of S, since A of S is a field. That is, A belongs to A of S. This A belongs to lambda implies A belongs to A of S, so lambda will subset of A of S. Put it as 2. From 1 and 2, lambda equal to A of S. First extension theorem. Suppose S is a semi-algebra of subsets of omega and P from S to close to 0, 1 is sigma additive on S and satisfies P of omega equal to 1. There is a unique extension P dash of P to A of S defined by P dash of summation I belongs to I Si equal to summation I belongs to I P of Si, which is a probability measure on A of S, that is, P dash of omega equal to 1 and P dash is sigma additive on A of S. That is, we have a probability measure P on S and we uniquely extend P to A of S, that is given by P dash, and P dash of summation I belongs to I Si equal to summation I belongs to I P of Si. Now we want to prove P dash is a probability measure on A of S. Proof. Given that S is a semi-algebra of subsets of omega and P from S to close to 0, 1 is sigma additive on S and P of omega equal to 1. We have to show that first one, P dash from S to close to 0, 1 is a well-defined extension of P to A of S. And second one, P dash is a probability measure. And third one, P dash is unique. Let A, B belongs to A of S. By previous lemma, we have A of S is the set defined by set of all I belongs to Si. I is finite. Si belongs to I disjoint and Si belongs to S. So A and B can be written as A equal to summation I belongs to Si and B equal to summation J belongs to J Sj dash. Here I and J are finite index set and Si belongs to I and Sj dash J belongs to J are disjoint subsets of omega. Now to prove P dash is a well-defined extension, suppose A equal to B. Then we will show that P dash of A equal to P dash of P. So consider P dash of A equal to P dash of summation I belongs to Si and that's equal to summation I belongs to I P of Si. Now Si equal to Si intersection A. Si intersection A is Si itself. and A and B are equal, Si intersection A equal to Si intersection B, and that's equal to Si intersection summation j belongs to j Sj dash, and that is equal to summation j belongs to j Si intersection Sj dash. Now consider P dash of A. P dash of A equal to summation I belongs to capital I, P of summation j belongs to j Si intersection Sj dash, and that is equal to summation I belongs to I, summation j belongs to j, P of Si intersection Sj dash, since P is additive on S. And interchanging the sum, we get this. And now summation j belongs to j, P of summation I belongs to I, Si intersection Sj dash, again by the additivity of P on S. And that is equal to summation j belongs to j, P of Sj dash intersection summation I belongs to I, Si. And that is equal to summation j belongs to j, P of Sj dash intersection A, since this set is capital A. And that is equal to summation j belongs to j, P of Sj dash intersection B, since A and B are equal. And that is equal to summation j belongs to j, P of Sj dash, since Sj dash intersection B is Sj dash itself. And that is equal to P dash of summation j belongs to j Sj dash by the definition P dash. And that is equal to P dash of B. That is P dash of A equal to P dash of B. P dash is well defined extension. Next we have to show that P dash is a probability measure. First one, P dash of omega, and that is equal to P of omega, that is equal to 1, since P dash and P are equal here. Second one, that A belongs to A of S, which implies A equal to summation I belongs to I Si, and P dash of A equal to P dash of summation I belongs to I Si, and by definition that is equal to summation I belongs to I, P of Si, but P of Si are greater than or equal to 0 for all I belongs to I, which implies summation I belongs to I, P of Si greater than or equal to 0. That is P dash of A greater than or equal to 0 for all A belongs to A of S. Next we want to prove third property, that is P dash is sigma additive. For that, let ai greater than or equal to 1 be mutually disjoint sets in E of S, such that summation I equal to 1 to infinity ai is in A of S. We have to show that P dash of summation I equal to 1 to infinity ai equal to summation I equal to 1 to infinity P dash of ai. For each I, since ei belongs to A of S, we can write ai as ai equal to summation j belongs to ji Sij, where ji is a finite index set and Sij j belongs to ji are disjoint for Sij belongs to S. Let's take A as the summation I equal to 1 to infinity ai, and which is in A of S, that is A belongs to A of S. Then A can be written as A equal to summation k belongs to k sk, where sk belongs to s, k in k, where k is a finite index set. Now consider P dash